I think we can start, although no one has joined. Maybe they will join eventually. So, welcome everyone. This is NOC 25W110 NPTEL tutorial session on microelectronics devices to circuits. Yeah. So, welcome. So, this is NOC 25W110 NPTEL tutorial on microelectronics devices to circuits. The course instructor is Professor Sudeb Dasgupta. I am Debashish from IIT Kanpur. So yeah, we go live every week Saturday on from 7 to 9. This is week 6. So let us begin. So it was mentioned, the question asks that consider a N-channel MOSFET as shown in the figure below. What will be the change in ID if VDD is changed from 3.3 to 1.8? I think it is 1.8 volt. Consider VTH of this, mu n Cox WL of this. Okay. So to solve this, we need to know the region of operation of the MOSFETs. So this we have discussed in the last session. So if we plot for an N-channel MOSFET, ID versus VDS, so I will get something like this, right? So, and there is something called, okay. So let me just, so this is the voltage below which you are at linear region this way, and this way it is saturation. Okay. So what are the key features of linear region? So linear region, you need to have your VGS greater than VTH. That makes your transistor in the on state. And another one is your VDS has to be less than something called VDS SAT. And this VDS SAT is nothing but your gate overdrive. That means VGS minus VTH. Fine. So this point is basically your VDS SAT or VGS minus VTH. So understand one thing, that this curve is for a fixed VGS. Okay. So let's say VGS is equal to your, in the question it is given 2.5 volt. Now if I change my VGS, how will the curve change? So for example, for a lower VGS, I will see something like this, right? This changes your VGS less than this. So please note this. And in this region or linear region, your current to voltage relation is mu n Cox dash W over L VGS minus VTH times VDS minus VDS square by 2. Okay. So this is your, so this quantity is your electron mobility. This is your epsilon ox by T ox or gate oxide capacitance per unit area. This area is nothing but your W times L. Okay. This is your transistor width. This is the channel length, and others are the voltages. Okay. Similarly, if you see your, let's say, saturation region, what do you need to have? You need to have VGS greater than VTH for sure, because you want your transistor to be on, and your VDS greater than VDS set, right? So now in the question, so we are at, so this value is what from the question? This VGS is 2.5 volt here, 2.5 minus VTH is your 0.5 volt. So VDS at is your 2 volt. Fine. So what is the first voltage we need to calculate the current for? Is 3.3 volt. So this is your 2.0 volt. So your 3 volt will be somewhere at higher voltage. So in this region, let's say, so this is, let's say, VDS1 is equal to 3.3 volt, and corresponding IDS1 is, this is your IDS1, right? And what is the next point? That is 1.8 volt. That is below this point. So this is VDS2 equal to 1.8 volt, and corresponding current is basically this. So this is your IDS2. So what they are asking us to calculate is nothing but this difference, okay, from IDS1 to IDS2. So for that we need to calculate IDS1 and IDS2. So now my IDS1, and by the way, in this region, the current does not depend on ideally the drain to source voltage. So this is basically, if you want to delete this, and so actually your curve is like this, flat, okay. So it will be like this, and then it will be flat if your, it does not depend on, that is basically ideal case when your channel length modulation or any short channel effects are not present. So similarly, just let me do this. So this is your lower VGS, okay. So now if I correct the point, so this will be your IDS1. Fine. So your, in this region, if you just put VDS equal to VD sat, you will get, this will be half mu n Cox dash W over L VGS minus VTH whole square. And for small channel devices, you have another term 1 plus lambda VDS, right? This will be multiplied for small channel or short channel devices. This is due to CLM, channel length modulation, right? So now in IDS1, we need to see what are the stipulation. My VDS is 3.3 volt because my VS is ground and this is my VD. So VDS is nothing but your VDD. So VDS is 3.3 volt, that is greater than your VDS sat. Fine. And what about VGS? VGS in both the cases 2.5 volt greater than your VTH, that is your 0.5 volt. So this situation is in saturation. So I will use this formula to calculate IDS1. So my IDS1 will be half mu n Cox W by L VGS minus VTH whole square. So now this quantity is given as 100 microampere per volt square. So half times 100 microampere per volt square times, this is your VGS minus VTH, you have calculated to be 2 volt. So it will be 4 volts square. So this gets cancelled. So now you have 200 microampere. Okay. So your IDS1 is 200 microampere. That is this value, 200 microampere. Now if you drop the voltage, so case 2 is your VDS is equal to 1.8 volt. That is less than your 2 volt, or your, you call it VOV or VDS sat or VGS minus VTH. So we are in linear region. Fine. So now here my IDS2, if I calculate, it will be mu n Cox W over L VGS minus VTH times VDS minus VDS square by 2. So this quantity is already given, 100 microampere per volt square. And what about VGS minus VTH? It is 2 volt we know. And then 1.8 minus 1.8 square divided by 2 volt square, right? So we'll have how much? Let us take 2 common outside, 200. So we'll have 1.8 minus 1.8 times 1.8, 2 times 2 whole square. So this will simply give me 0.9 times 0.9 is 0.81. So if you calculate this, it will come out to be 198 microampere. So what is your delta IDS? Delta IDS nothing but IDS1 minus IDS2, that is your 2 microampere. So what we needed to focus on? We needed to focus on the region of operation of the transistors. So this point is now 198 microampere. So this difference is nothing but 2 microampere. Okay. I think this is pretty straightforward. Now let us move to the next problem. So in order to have zero substrate bias effect, the substrate of a p-channel enhancement type MOSFET should be how much? Right? That is the question. So what do you think? So let us say, first, can you tell me what is substrate bias effect? Or in more generally, it is known as body effect. So I think only Ankit is present. Ankit, do you want to discuss on this?
So actually, I have little idea about this.
Okay, not a problem. So let us say you have a MOSFET. So I am doing the N channel part, okay? Because P channel, you will have a difficulty in understanding the band diagrams because I have not introduced to you the P channel. So let's say if I take a cut section along this line, so I will have something like this, right? These 3 regions, this. So this will be my N plus, this will be P substrate, and this is N plus, right? If I take this, let's say this is X and this is X dash. So if I take this is X and this is X dash, it will look like something like this. So in equilibrium, how will your band diagram look like? Your band diagram will look like this, right? This we have discussed. This is your
Yes, sir.
EC. So now what will happen in case of P channel MOSFETs? Let's say this is your P plus, and this is N. So how will that look like? So this becomes your P plus, this becomes N type, and this becomes P plus. So your band diagram will look something like this, right? This is your EC, and similarly you will have your EV. So in this case, the electrons will move. So electron is seeing some barriers to cross. But in this case, what is the carrier in P channel MOSFET? In P channel MOSFET, which type of carrier? Which type of carrier takes part into conduction? Any idea?
Holes.
So if it is holes, which band we should consider for transport, EC or EV?
EV.
So if it is EV, so if let's say these are holes, so hole energy increases when we move downwards in the band diagram, right?
Yes, sir.
So you see that in this case also, holes will see a potential energy barrier to cross, which we need to reduce by applying the gate voltage. So this is a little bit difficult for you to understand because we always plot the electrical energy in the y-axis. So that is why we'll discuss about the n-channel MOSFET, and analogically we'll just tell for what will happen in case of p-channel MOSFET. So let me add one page. Okay. So now there is another terminal, right? So this is your body terminal. So this is gate, this is source, this is drain. So there is another terminal called body terminal. So what happens? So far you have understood that you have seen that your body and source are mostly shorted. But what happens if we have a potential difference between them, right? So that is what is your body effect. Fine. So now if we just focus on this portion of the device, okay? So what we are seeing, basically we are focusing on this portion of the band diagram, okay? So
Yes, sir.
if I just draw this, so you see it will be something like this. So this is your basically channel. Channel is when it is formed, but I will use this term very loosely. This is basically p-type substrate even when there is a barrier, and this is your source, right? Now assume that you have a potential, that is your VSB, connected between these two terminals, right? So what will happen to the source scenario? So first thing is that this is the case when my VGS is less than VTH, right? Then I will have this energy barrier, uh, right? Now as soon as I increase my gate voltage, as soon as my gate voltage is increased, so this barrier
Barrier
will
will
start
go.
to decrease.
Yes.
So that means earlier my carriers were not able to travel through. Now they are more freely can travel over the channel. This is what was happening so far. That much we have understood, right?
Yes, sir.
Now tell me that what happens if I put the source terminal at a positive bias. So this is my EC, right? So will
Yes, sir.
EC lower or will EC be higher if I put a positive voltage at the source terminal?
It will be a reverse bias, so I guess it
No,
will be higher.
there is nothing to do with reverse bias. Think it in this way: source is a terminal, right? There is this energy. Let's say this is something EC of the source. So if I apply a positive voltage to the source, will this be lowered or will this be higher? By applying positive voltage, it will lower, right? Because it is electronic energy. So if I apply a positive voltage, so this source terminal will lower. Basically, now my bands will look like this. If I apply, let's say earlier it was, in this case, it was VGS equal to VTH. Let us call it VTH 0. So now what happens if I apply VSB? So this barrier will lower by VSB, Q times VSB, because I am applying positive voltage at the source. So it's all the energy, electronic energy will reduce. Now you see,
Yes.
even at VGS equal to VTH, what I should have? I should have this. So most of the carriers are now were flowing. Now if I apply positive voltage at the source, what I am seeing? I am again seeing that my carriers are seeing a potential barrier. Okay.
Yes, sir.
Now how do I ensure that my carriers now see can cross or does not see potential barrier? One solution is to further reduce the energy, further reduce the conduction band energy, further lower the conduction band energy in the channel. That means if I can make a situation like this, then my carriers can again move freely, right?
Yes, sir.
So how do I lower this one?
By increasing VG.
That means I need to increase my VG more than VTH 0. So now my,
Yes.
let's say in this case, my threshold voltage becomes VTH. Okay. So threshold voltage is what? The moment my barrier is very little or almost the barrier vanishes, that is by that gate voltage for which the barrier almost vanishes is my threshold voltage. Now do you see that if my VSB is greater than 0, then my VTH will be greater than VTH 0. VTH 0 when my VSB is equal to 0. And VTH is the actual voltage that I need to have. If I have a VSB positive, then I need to increase the gate more. I need to put more effort in the gate voltage to get the level of inversion or to form the channel. Fine.
Yes, sir. Yes.
So this is what is called your body effect. Okay. So if you have seen the equation of VTH0, so VTH0 is VGB where channel forms. So there are these components, right? VFB plus you have this 2 phi f plus gamma root over 2 phi f. Okay. This is what is actually happening. Or in other terms, if I tell you more conveniently, so the potential energy with respect to this or channel, or the potential energy at this point, or the potential at this point, is called psi s, or surface potential. Surface potential. This is the potential with respect to ground that the channel or this region sees. Okay, so it can vary. For example, in this between these two regions, the psi s changes. Okay, psi s is not a fixed value, and the way your gate voltage. So basically, this is what we have, right? This is your oxide layer, and this is, let's say, your depletion charges. If I just take a cut section along the device, and let's say this is your body terminal beyond this, and let's say this is your gate terminal. So what are the potential drops you will have? So this total value is your VGB. All the charges are present at this interface. Sorry, all the charges are present at the metal interface. So your a potential drop will happen across the oxide. So this is called your oxide drop. So you can use psi or V, whatever. It is just a symbol of voltage. And another potential drop across this. This is called psi S. So basically, your VGB has three components. VFB, the flat band voltage, that is basically resetting the everything to zero or making the bands flat. And then these potential drops, psi oxide and psi surface. So this is basically expressed as gamma root over psi s, this psi oxide. Okay, what is gamma? Gamma is nothing but your this over C oxide. This is a very easy derivation. In any of the semiconductor books you can find this. It is nothing but a voltage division, a series division between two capacitors, right? We have seen that there will be these two capacitances. This is C ox, this is C depletion. So nothing but the potential drop across these two. This is psi ox, this is psi s. Okay. So now your VTH0 is that voltage, that gate voltage, where your psi s becomes 2 phi f. Phi f is the Fermi potential or the bulk potential in the, basically your phi f is nothing but phi t ln Na by Ni. That means how it depends on what is the doping of your substrate. Okay, so plus 2 phi f plus gamma root over 2 phi f. Fine. Now by applying this VSB, I needed to increase the surface potential by VSB as well. I am seeing the energy band diagram. That is why I am seeing the lowering of the bands. But that means my psi s has to increase by this VSB value. So if I take care of VTH, so VTH will be nothing but your flat band voltage plus this psi s will be VSB plus, in this case also this psi s will be this plus VSB, because this is how much I need to increase my surface potential or lower my energy by, because I applied some VSB at between the source and body. So this is basically your VGB, right? At some VGB, let's say. So now if I want to calculate VGS, so what is VGS? VG minus VS, right? So can I write VGS is equal to VGB minus VSB? Is this okay? VGS is VG minus VS, VGB is VG minus VB, minus VSB is VS minus VB, right?
Yes, sir. Yes.
So then if I just take this quantity this side, so my VGS will become what? VFB plus 2 phi F plus gamma root over 2 phi F plus VSB. So this is nothing but my VTH. 2 phi F plus VSB. So now if I want to calculate it in terms of this value, so in this case, it does not matter if my threshold voltage is VGS or VGB, right? Because my source and body are both connected. Because in this case, my VSB is equal to 0. Fine. So VTH becomes VFB plus 2 phi F plus, let's say, gamma root over 2 phi F plus gamma root over 2 phi F plus VSB minus root over 2 phi F. See if this to this is okay. I have just added
Yes.
and
Yes.
subtracted this term. So now this becomes what? This quantity is my, this guy VT0,
VTH 0. Yes.
VTH0 plus gamma root over 2 phi F plus VSB minus root over 2 phi F. So this is what your body effect is all about. So for a positive VSB, so basically if your VSB is greater than 0, then your VTH increases. Okay. So this is what is called your body effect. Fine. So to eliminate body effect or substrate bias effect, what is the condition I should have? I can simply set this equal to 0. If I put VSB equal to 0, that means my VTH becomes VTH 0.
VTH.
So
Yes.
no body effect. Fine. So source and body, if connected together, there will be no body effect. Now the question asks that for a P-channel MOSFET, where should I connect it? So let us consider an inverter. So this is my VDD, this is my ground. So this is my, let's say, transistor P channel, this is my transistor N channel. So can you tell me what is this terminal? So this terminal is gate, this terminal is also gate. So this is your drain and this is your source, right? For the NMOS. What about
Yes,
the
sir.
PMOS? What is this terminal?
The upper one is source and the lower one is
The
drain.
upper one is source, the lower one is drain, right? Because for my PMOS or P channel MOSFET, my source has to be at a higher potential.
Yes, sir.
Now let's say I have another terminal, the body terminal. So to remove body effect, what should I do? I will just connect it to my source and I'll just connect it to my source, right?
Yes, sir.
So now can you tell me, for to eliminate the substrate bias effect or zero substrate bias effect, the substrate of an P channel MOSFET should be connected to which potential in the circuit?
Most positive because it is connected to VDD.
Most positive bias. Why? Because it should be connected to the source. And for a P channel MOSFET, source is connected to the highest potential,
Yes.
right? Okay. If that is fine, now this question is very tricky, okay? Let me first tell you that because I have kept some of the discussions. So far what I have discussed is VSB greater than 0. What about VSB less than 0? I have not discussed, right? For an NMOS. We'll see what is the issue there. So now can you tell me how do I solve it? So I needed to calculate VTH, right? Question is given that calculate the VTH of an NMOS transistor. Consider ID is given, R1 is given, VT0 is given, 25F is given, and gamma is given. Everything is given, right? So what do I need to calculate? So basically VTH is equal to VTH0 plus gamma square root 25F plus VSB minus square root of 25F. This is the formula. What do I know? I know this, I know this. I need to calculate this because I know this as well, this as well, this as well, right? I need to calculate my VSB. So VB I know, this is my body terminal, this is my source terminal, this is my gate terminal, and this is my drain terminal. So VB
Sir,
is known to me
I
1 volt. Yeah.
sir, how come I know VTH? Because it is said that I had to calculate VTH.
No, VTH 0 you know, right? This is VT0.
VTH I know, but I don't know the VTH.
Yeah, oh, okay, sorry, my mistake.
Sir,
So this is
sir,
what
but
I need to calculate.
sir,
Yeah,
Yes, yes.
sir, but VTH is T not now, sir, but VTH is
VTH is,
VTH is T not now, sir, but
I do not hear you properly. Can you please pick up once?
sir, but VTH is you said that VTH is proportional to VTH not now, sir.
Yeah, it is proportional, but you need to find out the exact value, right?
Okay, sir.
So this is the formula we have derived, right? In the last problem. So this is the same formula that I am using that we have just derived. The question is about the body bias effect only. Okay,
Okay, sir.
VTH 0 is known. VTH 0 is what? When your VSB is 0. Fine. Now you need to find out in under a certain VSB condition what is your VTH. That is the question. We will just simply use this formula. But the crux of the question is in a different aspect. We'll see. So what is VS? So I need to know VSB is equal to VS minus VB. So VB I know. I need to calculate VS. What is VS? How can I calculate VS? So you see this ID, where will the ID flow? Where does the drain current flow in a MOSFET of N channel?
Drain to source.
So this current is flowing in this path. So if I know the current across this voltage, this resistor, can I calculate the voltage across this VS?
Yes.
So VS is nothing but your 100 ohms times the current. The current
IDR1.
is 1 milliampere. So it is 0.1 volt. Is that
Yes.
clear?
Yes.
Surya Satvik, is that clear?
Yes, sir, yes, sir. Yes, sir.
So now what is your VSB? VS is 0.1 volt. VB is how much? 1 volt. So it is minus 0.9 volt. Right? Now if I
Yes,
put
sir.
it into this formula, so what will be my VTH? VTH 0 is 0.8 volt plus gamma is my 0.4 volt square root of what is 25F? I am using this formula, okay? 25F is 0.7 minus 0.9 minus square root of 0.7. So what is the issue I am facing?
Under square root we have a negative term.
So is that allowed? What
No.
what is square root of some negative term?
Imaginary number.
Imaginary means I times square root of
I.
mod A, right?
Right.
So this means it is not physically possible. So what people do generally, that is a very bad thing to do, and I'll tell you why. People generally take the modulus of this. They will take plus and they will take the modulus of this and then proceed for the calculation. I think most of you have done it in this way. Is that what you are doing?
Yes.
But you understand, right? This is not practically possible. If you see, so basically what is happening in this? So let me use a very different color. Okay. So for example, now your source is VSB is not greater than 0. Your VSB is less than 0. That means what? You will have a higher barrier like this. So now your electrons can pass, right? How? Why your threshold voltage will increase then? It is seeing electrons are seeing a valley, right? By having negative VSB, your energy will increase. So electrons are seeing a valley, so it will immediately pass. So your threshold
Yes.
voltage should lower. So why should it increase? So please understand that this is not a right thing to do. Okay? You can ask the what do I say? You can ask the examiner in the examination hall in the examiner that this is not a correct question. You will get full marks for that. Okay? Why I am telling you? So this is your MOSFET, right? This is your body terminal. This is your N plus, N plus. This is your P terminal. This is, let's say this is source. This is drain. This is gate. Fine. So let's say my channel is formed, right? Between this. So I will have a current flow. So now if I draw, this is my source, this is my drain, and let's say this is my body. So I will have a current source between these two. That is my IDS. Fine.
Yes, sir.
Now what about this body terminal? What do I see? What do I see? What components do I see here? Can you tell me the components? What do I see here?
There will be depletion region, so there will be, I guess I can model it by a diode.
You can and you should, right? This is
Yes.
nothing but a diode. You see, this is nothing but a diode. So you will model this as PN junction diodes. And what is the semiconductor used in this diode? These are the silicon diodes, right?
Yes.
Now assume a condition that your source is at 0.1 volt. You have increased your body voltage to be 1 volt, right? And let's say your VDD is very high, right? VDD is generally, it will be around 2 to 3 volt, okay? Let's assume that VDD is, because this VDD is the, for NMOS, it has to have, drain has to be connected to the highest potential, right? So let's say this is 2 volt. What is the condition on this diode? Is it forward biased or is it reverse biased? The drain to body diode?
Reverse bias.
Reverse biased. So this is reversed biased. Okay, no worry. Reverse bias, very minute current, no worry. What is the condition on this?
Forward bias.
Exactly. So this is your forward bias. There I have a huge problem. Can you see why? What is the
Yeah,
forward
because my
bias voltage across this?
IDS
What is the VFB? What is the diode voltage across this? What is VBS? VBS is 0.9 volt, right?
is
And diode is what? Diode is silicon diode.
0.7 volt is on voltage.
So that means if I just draw my IB2S versus VB2S, so your diode should have like this. This is your 0.7 volt. And where are you biasing it? At 0.9 volt. What will happen at 0.9 volt? Anyone? What will happen at 0.99 volt?
Possibly can reach 0.9 volt because the
It will
current
never reach,
is
right? Now you have applied a voltage source. For example, you have applied a voltage source. So voltage source, by definition, it has to hold the voltage irrespective of any current flowing through it. So almost infinite current will flow through it, right? Because this will reach this line at a very high current value. Do you think that much high current your device can sustain?
no
Your device will just burn out,
burn out.
right? So you see how beautiful the math is. You are getting an imaginary number and you are getting exactly an situation that is just not possible. You get the idea?
Yes, sir.
So where should I bias my this how far? So basically, ideally speaking, your source to body junction should never be forward biased. Okay, that is ideally. But how it will it help me if I forward bias it by a little amount? Forward biasing, it means VSB less than 0 is not possible. So how will it help if I make my VSB less than 0? VSB less than 0 will help me in reducing threshold voltage, right? For example, let's say my VSB is equal to minus 0.1. That means I am at around this region. This is acceptable for me, right? Very little forward bias. It is below the cut-in voltage of the diode. But how will my formula look like then? My VTH will be VTH0 plus gamma square root of 0.7 minus 0.1 minus root over 0.7. So this quantity will be negative. So I will have a lowering of threshold voltage, means more current I can get out of it. Is that clear?
Yes, sir. Yes.
So what is the condition I should have? So condition I should have, my VSB should never cross, VSB can never be less than
The
or
diode
your
cutting.
your not diode cut-in voltage. It should be around this 0.7 volt. That is what? That is your 25F, right?
Yes, sir. Yes.
It should never be less than, means your VSB is negative in this case, right? So mod VSB, how do I put it? So VSB less than 25F. So when VSB is less than 0. Okay. When
Yes.
VSB is less than 0, it has to be less than 25F. This is the condition we have to meet. So to be on the safer side, what we device engineers do generally, we hard code or by thumb rule is that your VSB cannot be less than minus 5F. Okay. Even we omit the factor of 2. We say that, so for a silicon diode, for a silicon MOSFET, the maximum you can bias VSB is around minus 0.4 to minus 0.5 volt. Okay. This is the maximum you can go for NMOS. Or in other term, if your source is grounded, if your VS is grounded, so your VB can maximum go 0.4 to 0.5 volt positive. Minus you can take it up to 2 volt as well. Okay. Minus there is no issue. So if I just plot a real line, let's say this is the line of VSB for an NMOS. So it sees a hard boundary at 0.4 to 0.5 volt, minus 0.4 to minus 0.5 volt, and positive direction it can go up to any value. Is that clear? So the question you will just blindly see and you will just use this modulus, which is not correct. Okay, you will get your answer by doing that, but physically you think by applying a positive voltage to the body, you are you are increasing the source side energy, right? That means your electrons can move freely or your threshold voltage should drop. Why will my threshold voltage increase? Right?
Yes, sir. Yes.
So that is one aspect of it. So what about this one? Given that this is this, so ID, everything is in saturation. So I'll use saturation formula IDP for
Sir,
PMOS. Yeah,
can you scroll down, sir? Can you scroll down?
yeah.
Thank you, sir. Okay, sir.
Okay. So IDP is half mu P Cox WP by LP VGS minus VTH P whole square. This is all for PMOS. And for NMOS, we'll see half mu N Cox Wn by Ln VGS minus VTH N whole square. Okay. Now, can you tell me that, so what I can see, my these are different, these are different, these are different. So why did I put my Cox same? There is no subscript of Cox. So what is Cox? Epsilon ox divided by Tox. So on a single wafer, if you pattern your PMOS and NMOS, no, your vertical direction or vertical dimensions remain same. So basically, this oxide layer will remain same. So that is why I will keep my COX dash same. Always remember that this COX dash does not depend upon the length and the width. It is the normalized to the area. Okay, otherwise what is the capacitance for a parallel plate? If the area is A, distance is D, dielectric is epsilon, what is the capacitance?
Epsilon A by D.
Epsilon A by D, right? But what we are taking here, we are removing the A. That means it is normalized. Understand this. So now in the question it is given that the channel lengths are also equal. We will see. So equal ID, that means I need to equate these two. So what I can omit? I can omit these halves, these COXs, these LPs, these overdrives are also same. So what do I left with? What am I left with? Mu P times WP is equal to mu N times WN, right? So mu P is equal to nothing but 0.4 times mu N times Wn. Mu N cancels. So your Wp over Wn becomes 1 over 0.4. What is this value?
2.5.
2.5.
So that is one aspect of the problem. Now can you tell me why mu P is greater than mu N?
Because electrons mu P greater.
We have discussed, right? What is mu? Mu P is Q tau by MP star, and mu N is Q tau by M electron star, right? So there are
Yes, sir.
two factors that are different in case of electrons and holes. So if you see your effective mass, M of P is greater than M of N. Even if you consider your tau P to be exactly in the same range of tau N, this is the major factor that contributes to that. What is M star?
Effectiveness.
And what is the expression of this?
H bar square root D2E by dk.
Do you know how this come?
Some concept of wave vector is involved.
Wait a second. Where did I add the page? Okay, I added it wrong. Anyway, so wait a second. Huh? Okay. Huh? What is it happening? Just a second. Okay. So this will be here. This will be here. Okay. Okay. Yeah. Some concept of what?
Wave vector.
That is fine, but you can understand it very easily. What is your what? First of all, why it is called effective mass? I have told you in the last class. Why effective? This is because we approximate the movement of electrons or holes in the crystal as if they are moving in free space. Okay, this I have mentioned in the last class. So what is the energy in the free space? What are the two components of energy? Potential energy and kinetic energy, right?
Yes, sir.
So in free space means what? There is no force of attraction, right? So there will be no potential energy. All the energy in the free space are kinetic energy.
Will be kinetic. Yes.
So this is my half mv square. This much you know, right?
Right, right.
So can I write it m square v square? So let's call this is p as in
Yes, sir.
momentum, right? So p is your linear momentum. This symbol is called defined as, okay? So p is your momentum. So now, and you know this formula equals to h nu, Planck's law.
Yes, sir.
So if I just write h by 2 pi times 2 pi nu, so can I write it h bar omega? This is my angular frequency,
Yes, sir.
right? So similarly, your momentum is your h bar k, okay? This can be found from Schrodinger equation. Very easy equation. Maybe in some other courses I have taught that. No, not for this course. Just note this one. So this becomes what? Energy becomes h bar square k square over 2m. So what is m? Can I write this? Okay. What is dE by dk? H bar square by m times k. What is d square E by dk square? H bar square by m. What is m? H bar square by d square E by dk square. Is that clear?
Yes.
So basically, what is the approximation? Where we are making the approximation of the effective mass? The approximation of the effective mass we are making at this place by assuming the movement of the electron and this as it is moving in terms of as it is moving in free space. So this relation this is basically h bar omega. So a relation between omega and k is called dispersion relation. Okay. So this is called somewhat parabolic dispersion relation. Anyway, these are just for your information. So why your mobility of this should be higher? Basically, if you draw the band structure of silicon, so you will have something like this. This is your conduction band edge, and you will have something like this. This is your valence band edge. So why did I draw it like that for silicon? Why this is not just this? Why did I draw it like this?
Because silicon is an indirect band gap semiconductor.
Exactly. Silicon is an indirect band gap semiconductor, right? So, and what is your this dE by this? This double derivative is called curvature, right? Where do the holes reside? Holes reside at this place because this is the lowest energy for the holes. Every particle likes to be at its lowest energy. And where does the electrons resides? Electrons resides at this lowest part in the conduction band. So this is your conduction band, this is your valence band, and these are the edges. This is your EC, this is your EV. Okay. So the curvature is basically if you take the double derivative at this point. So you see the slope is 0, right? But the curvature will not be 0. Do you see why? Because for example, you have a curve like this. Let's say this is your f of x. So what will be the derivative? So this will be 0 constant. Then here also you will have 0 and here also you will have 0. But in this case you will have a positive slope. In this case you have negative slope. So your slope is decreasing, first increasing, then decreasing. Here it is the maximum. So you will have something like this. This is your f dash of x. And what about the other second time derivative? So you will have something like this, right? These are your 0 points. So having a minima does not mean that your slope is having a minima means your first derivative is 0, but your second derivative is negative, right? That is the condition you find out to find a minima. So this curvature denotes that only. Okay. For a minima, so this is a minima. Your second derivative has to be greater than 0 and dE by dk has to be equal to 0. But in this case, your dE by d2E by dk2 is less than 0 because this is a maxima. So you see that the m star of P is negative.
Yes.
Right? So you holes are some particle, quasi particles. These are not real particles. Okay, this is just the absence of electrons. So this is just a model, how you model that. So that is why the m star is negative. Negative mass, there is nothing physical about negative mass. Okay, so this is just a manifestation of the fact that you have considered your absence of electron to be a particle. So in the first place, you have assumed that you have a particle where there is a void, right? That is why your mass is becoming negative. So note the salient points, okay? And don't get, how do I put it? Don't get very much surprised if you encounter this kind of situations. So that is why your m star P is more than m star of this, your m star of electron, and as it is coming in the denominator, so your mobility of P is lower than mobility of electron. Okay. We'll move on.
But in the question it is higher, right, sir? Mu p is greater than mu n.
No. What do you think?
Oh, it's lower. So, sir, I think the symbol you have drawn in that is greater than.
Oh, okay. Thanks. So mu p is less than this, and m star p is greater than m star electron. Okay, or m star n. Anyway, so let us move. So the CMOS inverter. Okay, we'll try to speed up. So the CMOS inverter can be used as an amplifier when? What is the
Both
answer?
operate. Sir, C option.
Why? C option.
Yes, sir.
Both operates in linear region.
Yes, sir.
Are you sure?
Yes, sir, I'm sure.
So this is not a right answer. So we'll see. So this is your inverter, right? This is your V in. This is your V out. So how will the output look like? This looks something like this, right? Have you seen this?
Yes, VTC, voltage transformer.
This is VTC.
Yes, sir. PTC, sir.
Yeah. So that means what? When you have a low input, your output is high. When you have a high input, your output is low, right?
Yes,
So what is the gain? What is gain? What is AV?
V out
It
by
is dV out by dV in, right? So by the way, amplifiers we always use in small signal terms. Okay, whenever there is small signal, we will just assume that we need to take derivatives. Okay, if it is a linear line, then you can take the derivative to be constant because the slope of the linear variation is constant. Fine.
yes, sir.
So how will the derivative of this curve look like? If I draw it on the same scale, so let's say I draw AV as well. How will AV look like? In this region it will be 0. In this region it will be 0, right? And at this point it will have the highest slope. So this is your AV. Is that clear?
Yes, sir.
Surya Satvik, is that clear?
Yes, sir.
By looking at the VTC, you should be able to plot the derivative, right? By looking at
Oh,
any plot, you should be able to plot the derivative qualitatively.
okay, sir.
Because here your slope is 0, then your slope is increasing. At this point, the slope is maximum. This is called the inflection point. Then again, your slopes are decreasing, right? And then again becoming 0. Basically, let's say you are moving from 0, then -1, -2, -3, -4, -5, and then again -4, -3, -2, -1, and 0. This is what is happening. So where can we use the amplifier as an use the inverter as an amplifier? Where there is a sufficient gain, right? So where there is a sufficient gain in this region. Okay. So this is the place. So this is the regions where inverter can be used as amplifier. Fine. Now we need to find out that how in device level, how from the device level we get these characteristics. Okay, otherwise we will not be able to understand why and what region the what is the region. So we will not be able to understand in this region what is the condition on the MOSFETs, in this region what is the condition on the MOSFETs, in this region what is the condition on the MOSFETs. Okay, that we need to find out. So did any one of you try to see how this VTC come about? Anyone? Or do you know how this comes about?
So you mean which region is which part
No,
of
no.
the current passing?
Why this VTC is like that? Do you know how why this VTC is like that? So this is your source, this is your gate, this is your drain, this is your drain, this is your source, this is your gate. Is this much clear?
Yes.
Let's say the current flowing is ID. So the same current will flow through NMOS and PMOS, all right?
Yes, sir.
So we will draw a curve. So okay, let me just copy this and do it in a fresh page. So we'll draw this. We'll draw V out versus ID. Okay. So fine. And parallelly, we'll draw V in versus V out. Okay. So let's start. So first thing for PMOS. So what are the two voltages we require to get the what region it operates for PMOS? What are the two voltages we need to know? The status of two voltages. Which two voltage statuses we should know?
VDS and VGS.
No, it is PMOS, right? We need to know VSG and VSD, right? That is the
Yes,
same
yes,
thing
sir.
if you consider the negative
Yes,
sign.
yes. PMOS
So
is
what is VSG? From the figure, can you tell me what is VSG in terms of VDD, V out and V in?
VDD minus V in.
VDD minus V in. Good. And what is VSD?
VDD minus V out.
And what about NMOS?
VGS and
VGS
VDS.
and VDS. So VDS is your V out and VGS is your V in.
V.
Is that okay?
Yes, sir.
Now let's say my VGS is this. Let's say this value is VTHN. Okay. What is that? Case 1 is VGS means basically V in is less than V threshold voltage of N MOSFET. Then what is the IDVD curve for NMOS? So what is the status of NMOS then? Linear or saturation? Okay, first start at, then first start at 0. Let's say your VTH, okay, just let's start at this. Tell me just if your V in is 0, what will happen? My NMOS characteristics. So I will draw this color with NMOS and let's say this color for PMOS. So where is my NMOS? This is my NMOS characteristics. And what is my PMOS characteristics? Let's mark this point as VDD. So what is my, if V in is 0, what is VSG of PMOS? If
VDD.
V in is 0, VDD,
VDD.
right?
Yes.
So I will have a characteristic something like this. VSGP is equal to VDD. Is that okay? Is that okay?
Yes, sir.
Now let us increase. Now let us increase V in to be less than VTHN. So where will my NMOS be? What is the state of my NMOS? NMOS will still be in cutoff.
Yes.
This line will remain same. But what about PMOS now? My VSG will reduce, right? So my curve will come down a little bit.
VDD minus some finite value.
Exactly. So my VGSG will be some VDD minus, let's say, VTHN. Okay. Some value, but the voltage will drop, right? But the current will drop.
Yes, sir.
Fine. So I want to find out this potential, this node's potential V out, right? And what I have two current sources. This is your NMOS. This is your PMOS. So how do I find out this node voltage? I need to balance the two current, right? IDP and this IDN, this will be equal because they are in series. So in this plot, I need to find out the intersection of the two currents, the blue currents or the NMOS currents and the red currents or the PMOS currents. Is that clear?
Yes, sir. Okay, sir.
Yes. Yes.
So what is the cross section now? This point. Have you observed?
Yes, sir.
So in this scale, what is happening? I have started with this 0 and now I am at VTN. VTHN.
Hello.
So till this point, what will be my output? My output will be VDD.
VDD. Yes.
Fine. Now let us take the another extreme case. For example, let's see case 3. My V in is greater than VTHP, and the fourth case is, let's say V in is VDD. So I am taking another case, this to this. So this is my VTHP and this is my VDD. So let us first consider this point VDD. So if V in my VDD, what is VSG of PMOS?
0 volt.
That means my this curve is in this line. So your VSG is equal to 0 volt, 0 volt to VDD minus, so this is my VSGP is equal to 0 volt to, let's say, VTHP, right? And what is
Yes.
the voltage? If it is VDD, VGS, so NMOS will have some high current. NMOS current will be like this. Similarly, so this is your VGS equal to VDD, and this is your VGS N equal to VDD minus VTP or VTHP, the threshold voltage, right? Please stop me if you have not understood till this much. And what is the intersection then? In this case, the intersection is this point. So V out is your 0. So in this region, your V out is 0. Is that clear?
Sir.
Yes,
Yeah.
Yes.
So earlier you understood that NMOS part, right? 0 to VTHN.
Yes, sir. Yes, sir.
Now you assume that you are starting at this point and going this way. So when you are at VDD, what is your VSG? VSG is 0, right? Or V in is VDD.
Yes, sir. It
So
is
if
0.
VSG is 0, that means your PMOS is in cutoff.
Yes, sir. Cut off.
So that is why your current will be 0. This red line is 0. This red
Yes.
line is the ID of
ID.
This red line is the ID of PMOS, okay? And blue line is the ID of NMOS. Fine?
Yes, fine. Yes, sir.
So if it is VDD, V in is VDD, so VGS is VDD. So NMOS is on, right? So NMOS will have this current.
Yes, sir.
Now assume a situation you are reducing your VDD from you reducing your V in from VDD to a value that is equal to the threshold voltage of the PMOS.
Sir, sir, but PMOS is proportional to NMOS, no, sir.
PMOS is
PMOS is you're showing. You said that red line is PMOS and blue line is NMOS, no, sir. But PMOS
right.
is
PMOS is
Sir, you said that IDP is PMOS and IDN is NMOS, no, sir.
right?
Sir, but the red line is touching blue line, no, sir. Then VGS is equal to
No,
VDP, no?
but those are at different bias conditions, right?
Yes, sir. Yes.
You understood, right? These are two
Yes, sir.
different bias conditions.
Okay.
So in these two cases, what was your V in? Your V in is VDD minus VTHP less than V in less than VDD. This is the condition for these two blue lines. And for these two red lines, the condition was 0 less than V in less than VTHL. Right? The conditions are different.
Yes, sir.
Now for the intermediate section, you can see that you can draw your lines like this for different bias conditions, right? Now let's say you want to find the cross section points, okay? For example, I am at this line, third line. So this third line will correspond to the first line of this. So let me just name it so that it will be clear for you. So let's say this is 1, 2, 3, 4, 5. Similarly, this will be your 1 and 2, 5, then 6, 7 is this line only. Similarly, this will be your 1 and 2, fine. This will be 3, 4, 5, 6 and 7. Fine. Now let us see where these lines are crossing each other. Okay. So for 6, 7 and 1 and 2, we know that these are fine. So this point is your V in equal to 0, right? V in equal to 0 is nothing but your point number 7. So this point is point number 6. And this point is point number 1. And this point is point number 2. Or I have done it in the opposite way. Okay, I have done it in the. So this is your point 1, this is your point 2, this is your point 6, and this is your point 7. Please tell me if this much is okay with you.
Yes, sir.
So now let us trace the third point. So this is my third curve and this is my third curve, right? So this line is crossing at this point. So just let me use, this is one point. Similarly, fourth line crossing at fourth point at this point. Fifth line crossing fifth, this 5 is crossing 5 at this point. Okay. So I have, let's say this is my third point, this is my fourth point, and this is my fifth point. I will have something like this. So this is my third, fourth, and fifth. Now let us bifurcate the regions. So in 1 and 2 point, N and P. So what is the status of at point 1? Where is point 1? Point 1 is here, right? So this is 1, 1, 2, 3, 4, 5, 6, 7. So for point 1 and 2, what is the condition of NMOS? For point 1 and 2, what is the condition of NMOS?
0 volt.
Zero current, right? Zero current
Yes, sir.
means cut off.
Cut off.
And what is the condition of PMOS?
Saturation.
It is just started, right? So that means it is in linear region.
Yes, sir. Yes, sir.
And in this region, what is the case? And similarly, let's say in this case, NMOS and PMOS. So in this case, your PMOS is in cutoff, NMOS is in linear region,
Yes.
right? Now, let us take point 3. So point 3 is in this region. So in point 3 or this point, what is the condition of NMOS and what is the condition of PMOS? NMOS, you can see it is in saturation, right?
Saturation and PMOS in linear.
And PMOS is in linear. Similarly, point 5,
PMOS saturation.
PMOS is in saturation, NMOS is in linear.
Linear.
So, Surya Satvik, are you able to follow?
Sir. Sir.
So, what about point 4?
Both in saturation.
Both in
Sir, both
saturation. So, what is the high gain region we have?
0.4.
0.4.
0.4, right? So, where should we bias it?
Sir, I have a doubt.
Yeah.
Sir, but the 50 point is also lowest point, no, sir. 15 is the lowest point on the saturation.
Sorry, 5th and 6th?
15 is the saturation cutoff, no, sir.
For which MOSFET?
Uh, NMOS point, sir.
N MOSFET, 5th
Yes.
point. 5th point is where? 5th point is here, right?
Yes, sir. Yes, sir.
So look at the line 5 of this and look at the line 5 of this, which region they are in. So this point in blue line, it is in the linear region, right?
Yes. Yes, sir. Sir.
And for red
Sorry.
line, it is in the saturation region.
Yes, sir. Sorry, sir. Sorry, sir.
So you see how and why it is coming?
Yes, sir. Sir. Sir, but colors are interchanged, no, sir.
Sorry?
Colors are interchanged, no, sir. I have confusion.
Oh,
Like,
okay. So now it is clear?
yes, sir. Yes.
Okay. So the answer is both has to operate in the saturation region, right? So Surya Satvik, the answer you have provided is wrong. So you need to clearly understand how your VTC is and why your VTC is, okay? And let me give you a further insight or further intuition for that matter. So when your device is, when let's say these are the two characteristics, okay? Let's say these are your NMOSs and let's say these are your PMOSs. Fine. So what is this difference? This difference is your input voltage, right? Because the input you are applying at gate, the gate voltage changes this difference. By changing the gate voltage, you go from one curve to other curve. And what
Yes.
is the change in output voltage? Change in output voltage is basically the difference between this, right? How much you are shifting in the x direction or along that line. So that is the output voltage. Now tell me one thing. Let's say two lines are crossing like this. Do you think then the gap of these two will be more if the slope of these two lines are more? Or if I give you something like this and two lines are crossing like this? So this is delta V2, this is delta V1. So which one will be more? Delta V2 is more than delta V1, right?
Yes, sir.
So I need to have the output characteristics crossing each other at its flatter portions, where these are flat. Then only I will have a huge difference in the output for a small change in the input. Okay. So that is why from intuition also you can tell that, yeah, in my saturation region the IDVD is flatter. That is why if two curves crosses each other for PMOS and NMOS, because the currents have to balance, so then I will get the most amount of voltage output, and that is why there the gain is more. But if it in case of linear region, so you will have very little, right? A straight line and two lines, how far you can give the output, but your y-axis shift is very little. Now you keep increasing the slope of the, now you keep decreasing the slope of the line. So you will start to have more gain at the output. Now if your two lines are very flat, you will get infinite gain. So that is the intuition behind it. So from that analogy, let me ask you another question. Which one is better? The red one or the green one? I have drawn two VTCs, right? The red one and the green one. Which one is better for an amplifier application? For CMOS inverter or switch applications, we know that the red one is better, right? Because my noise margins will be less, noise margins will be sufficient in case of the red one, or better in case of the red one. But what about amplification? You can see that I have a very high gain at the red one, right? Ankit or Surya Satvik, any comment?
Yes, radon has higher gain.
Right? Surya Satvik, do you also agree?
Oh, yes, sir. Yes, sir.
But that is not always the case, right? From the preference point of view. So what is the gain region in case of the red one? So let me just draw uh, what is happening? I do not understand. Okay, so let me just draw two VTCs. The red one being very steep and the green one being like this. So both of you have told that the red one is preferable because my gain is more in the red one. But what about the region of the gain? So this is where this is the region where I get non-zero gain in case of the green one, right? But in case of the red one, what is the gain region?
It will be very narrow.
So what is the issue there?
Any small change in the input can cause a large.
That
My
means
noise margin
what?
basically is hampered.
No, not noise margin. Let us speak from the amplifier point of view. So basically you need to have your signal or the small signal that you want to amplify between this range, right? For
Yes,
example,
sir.
this is your 50 millivolt sine omega t. So can you amplify 100 millivolt sine omega t with this? A signal that is like this. Can you do that?
No, no, sir.
Your signal will get lost at this region, right? Because in
Yes,
this case, this portion of your signal will just be
will be
lost.
lift off. Yes.
So high gain is beneficial in inverter designing where your signal is sufficiently small. But if you want to amplify a sufficiently larger signal, you need to have some room. Okay. So you cannot say which one is better, the red one or the green one. It is up to the preference. So whenever these kind of questions will be asked to you in your future interviews, so be aware of these things. Okay.
Sir, can you explain on this, sir?
So you have seen the, so you have understood this much, right? The red ones amplification limit is very little. So basically, let's say I have this much. Okay, this is my gain, this is my VTC. So I have a signal which is this. So what will be my output? My output will be this, right? Do you understand this much?
Yes, sir.
So this is the gain region. Your V in is getting converted to V out. Now you assume your signal is like this. How will your output look like?
Sir, but sir, it is on PMOS now, sir. It's like a PMOS now, sir.
What is like a PMOS?
The curve is like a PMOS now, sir.
No, no. This curve is V out by V in.
Oh,
This is basically what we are trying to do. This is your VDD. This is your ground. We are trying to apply a signal here. This is your V in. This is your V out. We are trying to amplify this, right?
okay, sir.
You understood, right? This is the VTC.
Yes, sir. Yes, sir. Yes, sir.
So there is a trade-off between these two. Okay. I think that is enough said on this. So I think you will
So
not now, yeah.
is this what is called the voltage headroom? There is some term I have read in that kind of book. Is this
Sir,
the
I
No,
have
voltage?
also read it.
no, I do not know if it is called voltage headroom, but it is called, voltage swing.
Sir, what is difference between voltage source and voltage swing, sir? What's the difference of it?
Voltage source and voltage swing.
Yes, sir. Yes, sir.
So voltage source is, so if you plot your IV, so what is a voltage source? What is the definition? Voltage source is something which will hold a fixed voltage across it irrespective of the current flowing through it, right? That means it has a fixed voltage irrespective of the current flowing through it. That means current can be any value, this value, this value, this value. So if you plot the trajectory, so it will be a straight line in a IV characteristics, it will be a straight line with a slope of infinity, right? This is what a voltage source means. Voltage swing is across a DC value, how large your voltage can swing. For example, if this is your 2 volt, so your voltage swing, and let's say this maximum room possible, just like I have said here, right? For the rate curve, what is the voltage swing maximum possible? Is your 50 millivolt peak to peak. That means if you increase your signal more than 50 millivolt, your signal will get clipped, right? Clipped means some portion of the signal will get lost. The high magnitude signal will be lost. So now suppose you are using some amplitude modulation, right? Where your modulation or the information of the message is embedded on the amplitude of the signal itself. Now think that your higher amplitude signal is getting clipped off. That means what? That means your message is getting lost, right? So that is you cannot afford. That is why we also want that as a circuit designers, we want my voltage swing to be very large. Voltage swing and voltage source are completely two different concepts. Okay, fine. I think the sizing. So next, so inverter so far you have done. So now next session we will do delay and power optimization of inverters. Okay, what is delay, what is power, and we will try to optimize them. Fine. And we will say what are the, we will see what are the critical aspects and how to do that. So this delay will completely be determined by your RC time constant. And power, we'll see, power is a little bit easier, but I would say the understanding will be a little more trickier. But delay you will understand very easily. So you understand one thing, that any delay in this world can be modeled using a RC network. Okay. For example, if you are boiling some water, no, so your temperature is in that rate of increase of temperature is not linear. It takes some time to transfer the heat from one position to another, right? One temperature
Yes.
to the another. So this is there is a time lag basically. So that also you can model using your RC network. Okay, these are some of the very advanced concepts. But by the way, just to finish on this note, why do we study electrical engineering or electronics engineering? Any idea? What is so special about electricity? We can discuss. What are the forms of energy known to you? What are the types of energy? Anyone? I believe both of you are from electrical or electronics background. Ankit, Surya, Satvik.
Yes, sir. It's different types of energies. There, heat energies, there, electricities, kind of energy.
Electricity, solar energy, then
Solar.
your nuclear energy, hydro energy, right? So why
Yes.
we are obsessed with electricity and electrical energy? Any idea? You can take a guess, right? I just want to know what you think on this. So the concept is that among all the energies present known to humankind, electrical energy is the one that we can control to the utmost precision. Okay. That is why most of your energies are converted to first electrical energy, then all the signal processing and energy processing is done in electricity, circuits, currents, and voltages, and then again convert it back to the other form of energy and then live out, right? For example, when you are
Transducer.
early, yeah, transducers, exactly, input transducer and output transducers. For example, earlier we used to cook, right, with the this wooden ovens, right? But what was the
Yes.
issue? The temperature we were not able to control precisely. So now what did they invent? They invented these induction cookers, then invented microwaves, right? So
Yes.
why the electrical form of energy? Because electrical form of energy can control to the utmost precision by human being, right?
Yes, sir.
So appreciate the fact that why you are doing the course of electrical engineering or electronics engineering, right? So this is the main reason for the importance of the electrical or electronics engineer. Okay. So I think we can close on this note, and next week we'll do the delay and power optimization problems. Maybe we'll touch upon logical efforts and all. Yeah.
Sir, I want some suggestion that can you please suggest some book on which I can read the physics behind the MOS that you are discussing, the band voltages or something like that.
Okay. I can. Okay. Just let me write it down. So there are two books in undergrad. You are undergraduate, right?
Yes.
So there are advanced books for PGs, right? Where you can go into as much depth as you want. Even you
Yes.
can derive the Schrodinger equations because everything comes from quantum mechanics if you want to understand. But for basic simplicity, I'll suggest you semiconductor device fundamentals and advanced semiconductor. So this is more, the basics of your how your band structure, band diagram, everything comes about. And this is more on the device aspects. So both are written by Robert Pierre of Purdue University. Okay. In your
Can
UG,
we refer those books?
sorry,
Can we refer those books, sir?
can you?
Sir, can we refer to those books, sir, for exam?
No, no. He is asking me about how to clear the concepts, right? So
No,
at the
sir,
UG, yeah. Okay.
sir,
Your question is, can you refer these books for the exams?
yes, sir, yes, sir.
So see, exams, how do I see it that if you, for exams, I would suggest you stick to the course structure, okay? You watch Professor Sudeb's lectures and all, and then practice the problems. That will help you in getting marks in the exam. That is one aspect.
Oh,
Even if you
okay,
get 100 out of 100, do you know the 100% of the course? No, right? So he is asking about how you can improve the understanding of the subject.
okay, sir.
So I think these two books should be sufficient for you to give a head start, and then you can follow. If you choose to pursue post graduation, then there are ample of books, right? There are very good books on SMZ, right? But you will not understand anything now. These books are very abstract. Then there is Professor Sanjay Banerjee and Benji Streetman's book. Banerjee Streetman is there.
Treatment energy. Yes.
So Streetman Banerjee, if you read now, I think Banerjee sir has improved that book a lot in the 7th edition. So if you are able to get hand of that, that is fine. he told me that it is much improved now. So you can do that. Or but I would suggest that these two books should be your first on the first two books you should read in undergrad, right? Then proceed to these books. Energy statement is very good book, but maybe the writing style is such that you should know, you may not find it comfortable enough, right?
Okay, sir. Thank you. And if you can suggest some YouTube playlist or some kind of video lectures.
Can you do one thing? I cannot suggest it on this forum. Can you
Okay.
just drop me an email so that I'll give you the resources?
Okay, sir.
This
No
is
problem.
my email ID. DEBASHISH21 @iitk.ac.in. Okay. You just email me asking for the resources. I'll provide you. Okay.
Okay, sir. Thank you.
Yeah. I think
Thank you,
let's
sir. Thank
close
you
this
very much.
session.